Hello, this is Radiosity. I'm going to give a presentation on Radiosity surface details and textures. Let's go into the topic now. Let's see the overview of the presentation. We see Radiosity, its definition, intensity, radiant flux, the Radiosity equation, methods of adding surface details, the examples and charts. And we're going to see texture mapping, bump mapping, frame mapping, environment mapping, non-photorealistic rendering, an application of all these mappings and renderings, and see what are the advantages and disadvantages of these things. Let's go into the details. What is radiosity? Radiosity of a surface is defined as the rate at which energy leaves that surface. In photometry, that says as the amount of photons leaving a surface per unit time and unit area. In graphics, radiosity is also defined as an application of solving rendering equations for scenes which reflect light. This is not similar to Monte Carlo algorithm. Only parts of light source and the light that is reflected is concentrated in radiosity. There is another definition here. Radiosity is a global illumination algorithm in the sense that the illumination arriving on a surface comes not just directly from the light source but also from other sources reflecting light. This is an example. See the image. The image in the early stage is darker. After applying radiosity, the light that's not only coming from the source, the light getting reflected from different surfaces illuminate the total room. You can see the difference from the darker and the lighter stage in the picture. You can see the color bleeding too, just watch at the ceiling. There you can see green, red shades like that. This is called color bleeding. This comes from different surfaces which reflect light. Let's see the radiosity algorithm then. Radiosity is implemented in two different ways. One is the progressive radiosity, the other is radiosity shooting. When we come to progressive radiosity, this is done in iterations, and this is cumulative. An iteration depends on its previous iteration. For every bounce, the change in scene is observed, and after that, next pass is decided. So after many iterations, we will see whether the image is stable or not. If the image reach its final quality, the finest quality and stability, then we stop the iterations and we render the image like that. When it comes to shooting, this is not cumulative. Shoots light from the path, which just from the light source itself, and then it takes the light from patches which is being reflected. For each pass, we'll see the light which comes from the reflections, and then we'll finalize the image. For both algorithms, finally the lighting is seen and iterations are stopped. Thus, a well-lit image is obtained. What is intensity? Let's see about intensity now. Intensity is the property of the source. It is definable from a point source of light. Its dimension is power per solid angle. It is the radiant flux emitted, reflected, transmitted or received per unit solid angle. So let's see what is solid angle. It is a 2D angle. Is it? Yeah, it's a 2D angle. It can also be explained like this. How big an object is from the perspective of a viewer. It doesn't have any units, it's just a number. So what is radiant flux? We'll see radiant flux in the later slides. So let's go to the next slide. Yeah, we've just seen about solid angle. I told you this is a two-dimensional angle in a three-dimensional space. It's the view from a viewpoint how large an object looks. What is intensity per solid angle? I told you the power flux per unit solid angle is the nearest precise terminology to the common term intensity. You can see the figure. It shows you the solid angle, the light source, and the point of view. What is radiant flux? Radiant flux is the radiant energy emitted, reflected, transmitted or received per unit time. It can also be known as energy per unit time that is radiated from a source over wavelength. What is irradiance? Irradiance is a flux per unit area. The number of photons passing through unit area is called irradiance. That may be incoming or outgoing. Incoming means receiving light from a different light source, or outgoing means reflecting a light from a different light source or emitting self-light like self-luminous objects. What is form factor? Let's see form factor now. Form factor is also called view factor. This is a fraction of radiation that leaves a surface and hits another surface. If there are two surfaces, each surface reflects the light which falls on it, and these reflected lights may fall on the other surface. Then we see the form factor between the two surfaces. It is also known as the visibility of patches for each other's surfaces. If there is any obstacle in between them, the visibility narrows. If the obstacle completely blocks the path of the light, then the visibility factor becomes 0. If partially blocks, then it lies between 0 and 1. If the obstacle doesn't block any path between the two patches, then the visibility factor is 1. That means nothing is being blocked in between these two surfaces, and the light reflected from each surface is completely going to the other surface. Let's see the radiosity equation now. As seen in this, the radiosity equation is Bfx dA equal to this blah blah blah, and where the total radiosity is, as I told, is the total energy leaving small area. So we integrate this with area so that we will get this for the whole area. Let's see this one. This slide shows us the radiosity equation for diffuse surfaces. Here, if we assume that the finite number of patches are available in the total environment which we are looking into, then this equation is for calculating the radiosity. If the number of patches are finite, then it becomes like this. Form factor computation. We have seen form factor in the earlier slides, so let's compute that now. Form factor basically depends on two parameters. One, that's the distance between the two surfaces which we are going to calculate the form factor for, and the second one is the orientation of two surfaces with respect to each other. So the formula is this. The equation shows that form factor of surfaces between surfaces 1 and 2 is equal to 1 by area of surface 1, integral using area of surface 1, and then integral using area of surface 2 cos theta 1 and theta 2, where theta 1 and theta 2 are angles made by the surfaces with their normals, by r square. R is the distance between these two surfaces viewpoints, and dA1 dA2, that means for the integrals of area. Let's see the next slide. In this is form factor computation for diffuse surfaces. For diffuse surfaces, form factor turns out with an extra elements in the equation. That is, the area of the first surface is pi times its actual area in this equation, and then we add the visibility factor at the end. This visibility factor, as we have seen earlier, ranges from 0 to 1, depends on the light moving from this surface to that surface, whether there are any obstacles or not. So let's see what's progressive refinement. Progressive refinement is a special rendering technique which makes it possible to render a coarse version of the 3D scenes which is refined over time. What does this mean? As its name indicates, it is refinement over time. The 3D scene rendering is done until reaching the finest quality. When stability is reached, then the refinement stops. See this figure. Showing the light from a light source and the reflections on the surfaces which helps lit the room eventually. I mean, when only a single light source is present, at the beginning the room is not well lit like this which is shown in the figure. After the light being reflected, eventually the room becomes well lit. When stable lighting is reached, then it stays like that forever. So this is an example for progressive refinement. You can see three different levels of refinement. At first it's very dark, and then eventually the light being reflected from different surfaces, and then you can see a well lit room. So this happens after 3 passes as mentioned there. Let us see the applications of Radiosity now. What are the applications of Radiosity? Radiosity is widely used in the field of architecture. It is used for the design of structures and their interiors. Since ray tracing cannot be used for this purpose, Radiosity is a choice. For the estimation of lighting inside a construction to be known virtually, Radiosity is used. These have a great realistic feeling. They help in the reduction of testing costs. What are testing costs? When you're trying to design a new structure or new interior for a construction, you have to check which one suits best for your construction. If you do that using this technique, that would just be the soft thing. You need not spend more money for buying the testing things, and you need not test that. Actually, you can test that virtually by using the Radiosity techniques. So let's see the other one. Yeah, these applications have third-party add-on effects too. We have access to different libraries of different ambience materials, materials used for construction, and libraries of different lighting effects. These can be added for this Radiosity simulation, and when the design is simulated, you can virtually see how the design looks after construction, so that you can decide which material you should use, which kind of lighting you should use according to the construction you are making, and that saves you a lot of money, and that gives you the best apt construction to your taste. What are the examples of this application, like the architecture? Amphitheater design simulations, how an amphitheater should look, how people likes it. You can just check it virtually and then construct it. Lighting simulations for large events. The large events you can't expect without any chaos. So if the lighting is perfectly alright, you should then check the simulation for lighting before you implement that. Another example is like the home theater lighting designs, how the home theater looks. All these are examples of pretty much applications of this Radiosity. Let's get into environment mapping. This is proposed by Blinn and Neville in 1976. In computer graphics, environment mapping is efficient image-based lighting technique. It is a process of approximating the appearance of reflection of the surroundings on an object in that surroundings. So this is very significant because ray tracing is very expensive, while this one gives you at a very cheaper cost. You can't ray trace the whole picture, the whole surrounding to reflect that image on an object, which needs lots and lots of memory and which needs lots and lots of computation also. So when it comes to environment mapping, since you just need to compute the picture 2D image of the environment or surrounding, and then map it to the surface of the object so that the environment is being reflected on the object. It's that much easy. So what are the assumptions for this? There are two assumptions. One, the object doesn't reflect itself. That's the first assumption. And the second is the environment is assumed to be far away from you, like infinitely far, so that complete environment is being reflected on the image. So what are the types of environment mapping? There are three kinds we are seeing in this presentation. First one is spherical mapping, second cubic mapping, third Hill-Pix mapping. Let's see spherical mapping. Sphere mapping or spherical mapping is reflecting an environment on a object which is like a sphere or almost a sphere or equivalent to a sphere. So we assume that the environment is infinitely far away from the object. So we see the image, we make a 2D image of the environment and then map it to the texture of the object so that the reflection can be seen on this. The image texture is taken from perfectly reflective sphere which is viewed orthogonally from the eye. How is this done? First, the environment is reflected over a sphere. As we know, this is called spherical mapping. The environment first is reflected over a sphere and then it is mapped to the object. The 3D reflection is considered as a 2D image for mapping to the object. So some portion of reflected picture is not used since if the object is a subset of sphere. If it is a whole sphere, then all the part of reflection can be used. But if it is not a whole sphere, everything is a subset of sphere. So some part might be missed, not used. This is how working of spherical mapping. This is an example of spherical mapping which shows the environment being reflected on a coffee mug. You can see if it is a whole sphere, the complete environment is being reflected. But if it is not a whole sphere, or if it is so in this case this is a jug which is subset of a whole sphere, so it shows us that some part is being missed in this. Let's get into cubic mapping. Cube mapping is the process of mapping the environment with all 6 sides of a cube. I mean, the cube has 6 sides, so every side has its normal reflection on it. I mean, the surrounding is reflected on 6 different sides of a cube. It's completely rendered from viewpoints perpendicular to all sides of the cube. Then all the 6 can be unified. See, this is the working. I mean, this is how cube mapping is done. This is an example. See, the sky and the ocean are reflected on a cube in all the 6 directions. So let's see the differences between cubic mapping and sphere mapping. What are the problems with sphere mapping? Image distortion. And for sphere mapping, viewpoint dependency. You know, if we look from a different viewpoint, the image should look different. But in sphere mapping, the image after being mapped to the object is independent of perspective. So that's a disadvantage. And computational inefficiency. Cubic mapping is very much easy being computed when compared to sphere mapping. Let's see Hill-Pix mapping. This is another kind of mapping. It's called hierarchical equal area isolatute pixelization. Hill-Pix is the acronym for this. As its name indicates, this is a mapping of the environment over a 2 sphere. This pixelization can be thought of as mapping the sphere to 12 square facets on the plane followed by binary division of these facets into pixels, though it can be derived without using projection. Hill-Pix mapping is similar to other polyhedron mappings but can be hierarchical, thus providing a unified framework for generating polyhedra that better approximate the sphere. This allows lower distortion at the cost of increased computation. This is the example of Hill-Pix mapping. So this is actually a 4 square one which is then cut and divided like this. What are the applications of Hill-Pix mapping? This is very significant in large scale. I mean, this is used for cosmoanalysis. Prestigious organizations like NASA use this for analyzing space. Widely used in cosmology for storing and manipulating maps of the cosmic microwave background. What are the limitations of sphere environment mapping? You can see in this image, actually the two objects are in touch with the glass sphere. I mean, the cuboid and the sphere are in touch with the glass sphere. But as we can see in the reflection, those are not like touching the sphere. Those are not showing that these two surfaces are touching. That why is this happening? Because as I said you earlier, as we are assuming that the two objects, the environment is very far from us, so the cuboid is being shown that it is far away from the sphere. It's not touching the sphere. The assumption leads to this problem. What is texture mapping? Applying texture to a 3D object by mapping a 2D image to it is called texture mapping. It's that much pretty simple. How? Let us take a 2D image and wrap it around a 3D object. Thus, we can create texture on an object. It's like applying veneer or wallpaper to a real-time object. What are the types of texture mapping? There are forward mapping and inverse mapping. Forward mapping, as its name indicates, first we compute the 3D positions of the texture and then map them to the surface of the image plane. Inverse mapping, it's reverse to the forward mapping. First selects the pixels in the image plane, finds the corresponding point that maps a pixel in the texture plane, and then project them to that. Map the pixels and project the texture. What are the limitations for both of these? I mean, the limitation for forward mapping is the texture points next to each other may get to non-adjacent image points, which results in colorless region. For inverse mapping, aliasing is a big drawback. What is aliasing? Aliasing is pattern formation which is adverse for the rendered graphics. Since rendering is a sampling process, aliasing is a very common problem in graphics. Different kinds of aliasing are like edge jagging, false texture patterns, etc. How to overcome? How to overcome aliasing? We do anti-aliasing to overcome aliasing. Let's see in the next slides. See, these are the examples of aliasing. This is a jagged profile. I mean, this is the original image. You can see a curve like this. I mean, the black color is still half of this square region and the orange is here. But when you see here, as we are sampling the pixels and mapping them, the pixels turn out to be like this. The rendered image becomes like this, which is quite different from the original image. This is a problem of aliasing. This is another example for aliasing. The same thing happens here. We lose the details. As this takes the pixel color which has more in the area. I mean, in this square, yellow is more and black is less, so it takes yellow. In this square, black is more and yellow is less, so it takes black. This is loss of detail. This is one more example for aliasing. What is anti-aliasing? Anti-aliasing, as its name indicates, is a process of avoiding aliasing. Excuse me. There are different stages of anti-aliasing techniques. They are pre-filtering, post-filtering, super sampling. This is an example of pre-filtering. We can see this problem right here due to aliasing, and after applying pre-filtering, that goes better like this. What are problems being faced by anti-aliasing 2? Magnification and minification. What is magnification? See, when we get too close to the image, the texture pixels, which are also called texels, can be individually seen, so that we see the image like pixels, like boxes. What is minification? When the pixels are too far from the viewing point, for example, if we go too far away from the viewing point, a group of pixels combine together and look like a single picture. This gives loss of detail. So we lose details if group of pictures combine together and form a single picture. The picture doesn't look how it should look actually. How to resolve this problem? How to resolve magnification? There are different sampling effects which can resolve magnification, like point sampling, bilinear sampling, bicubic sampling, etc. For minification, MIP mapping. MIP mapping is a very significant technique to reduce minification. This is the example. You can see the MIP mapped point sampling, MIP mapped linear filtering here. This is the image without that, but this is quite better after MIP mapping. What are the applications of texture mapping? You can see the image here. This is the tomography of a fingertip. This helps in imaging sections and sectioning of different particles, this helps in radiology. What are other applications? Molecular graphics, giving textures, knowing the textures of molecules and rendering these images for the use of chemistry and physics. So let's get into different mapping techniques now. Bump mapping. What is bump mapping? Bump mapping is similar to texture mapping. The difference is texture contains colors and bumps contains bumps. These are height fields. This gives height to an image at certain parts. The field has some height or depth. This can be reached by perturbing the surface normals of the object and using the perturbed normal during light calculations. Let's see how. This is the example. See, the normal image looks so soft that doesn't have any ridges and grooves. In this case, we call those bumps. See, this is the rendered image after bump mapping. You can see all those bumps, like the ridges and grooves. Some parts it's high, some parts it's low. This is due to bump mapping. This looks more realistic, right? So let's see non-photorealistic rendering. What is NPR? Non-photorealistic rendering is a stream of computer graphics which points on expressing digital art in a wide variety of styles. So we want this not to look like real picture. We want this in artistic style. We want this in mosaics. We want this in different artistic styles. To create pictures that are result of imagination and not of the real world. We want illusion. We want abstract. So all this comes from non-photorealistic rendering. Let's see what are the different kinds of non-photorealistic rendering. Toon shading, shading the cartoons, painterly rendering, line drawing, hatching, silhouette tone detail, stippling, stroke textures, mapping techniques. All these are different kinds of NPR techniques we're going to see. We see some of them actually. Stippling. As you can see the image, stippling is a technique using dots. Several dots are combined to form a picture. If you need a darker position, you give the density of the dots is higher. Look at the eyelids, eyebrows of this woman. You need this area darker, so use more and more dots here. The density of dots is high in this place, in the place of eye. But in this place you want it lighter, so the density of dots is very less, so that you place dots very far from each other. Thus, creating an image using dots is called stippling. Let's see hatching. What is hatching? Hatching is also a kind of drawing technique which uses lines to form image. See, what we used here to form an image of, let's say this is the moon. To form the image of this, we use just lines. These are just lines. So this kind of drawing is called hatching, in which only lines are used. The arrangements of strokes can enhance perfection of the object shape. I mean, if the strokes are harder here and it's arranged in a style like this way, this makes it look like a 3D object, right? This is giving some height and depth there. This is called hatching. What's cross hatching? In hatching we have seen that we use only lines in a direction to draw an image. But in cross hatching, this is similar to hatching, but it is used using lines which are crossed to each other. You can see lines in this direction and lines in this direction too. So the lines using the crosses of lines, we create an image. This gives a better perspective and better view and height and depth to the image and looks like a good 3D image. Pen ending techniques. Pen and ink. What are pen and ink techniques? As we all know, drawing with a pen is not so easy because we can't erase that and we can't lighten that if we draw once. If the ink is drawn on the paper, you can't lighten that ink because we don't assume that it has any color. Let's say a white paper and a black pen. You can't lighten once you draw on that. What we have to do is put a less pressure on it to draw lighter lines, put more pressure on it to draw darker lines. So to cover large area, it's very difficult with the pen. So everything depends on strokes. Each stroke defines the image. If you want the strokes to be lighter, you draw lighter. If you want the strokes to be, let's see this image. This area is very dark. This part also is very dark. And when it comes to this part, this looks lighter. This looks lighter. So if you want that to look lighter, you just use a single stroke or you just use strokes with very less pressure. When it comes to this area, use multiple strokes with high pressure so that this looks so dark in the image. This is called pen and ink illustrations. So what is artistic rendering? Artistic rendering is the application of visual art styles to rendering. It's applying visual art while you are rendering in computer graphics. An image is taken first and then it is rendered to a certain art theme and a certain abstract level. You take a raw image and you fix that you just want to make that image look like kind of theme, and you fix a level of abstractness. So you combine all these three and make artistic rendering. This is also a non-photorealistic rendering. This helps in simplifying technical illustrations, like if you want to illustrate a new concept to people, artistic rendering will be very helpful so that the thing which you are going to convey to people can be easily understood even to nerds. What is rendering with mosaics? Mosaics are small pieces of stones or glass which are used in the artworks. The rendering process with mosaics make the image look like an image made of mosaics. The requirement is the mapping of mosaics with the image. So in the mosaic rendering, we map samples of mosaics to the texture of the object so that looks like a rendered image with mosaics. This is the example. See, eventually mosaic rendering increased in these three images, and that looks some NPR technique, some NPRistic style can be viewed in the final stage. Rotoscoping. What is rotoscoping? This is a process of making an image look like a shadow on a frosted glass. See this image. The original image is like this, and the final one looks like a shadow on a frosted glass. When you draw something on a frosted glass, or when you see something on a frosted glass, that looks like more like pixeling, or there are less details of the image that gives more color patterning, giving more hardness to the picture. What are the problems of rotoscoping? Boil, shake, which gives the image, not the original image effect, because when you trace the object, you are tracing a shadow on a frosted glass, so you have to trace it very carefully. So this can be avoided by careful tracing the job very carefully by experts, or sometimes boil can also create style to your picture, can also depict rotoscoping image. This works fine also. This is the example we have seen. These are all the references of my presentation. I used all these sources to create this presentation. And finally, thank you so much for giving me this opportunity.